Welcome to lecture 7 of module 5 on the subject microcontroller and embedded systems. Subject code is 15EC62 or 17EC62. So in the previous lecture we discussed about preemptive shortest job first scheduling, right? Preemptive SJF scheduling, or it is also known as shortest remaining time, preemptive SRT. So both are same. So we saw how it worked, and we discussed that using two examples in the previous two lectures. So now we shall talk about preemptive round robin scheduling, RR. Preemptive round robin scheduling. So what will happen in this is each process in the ready queue is executed for a predefined time slot. This is what will happen. So there will be a predefined time slot. So this time slot is also known as time slice. Okay, so this time slice is OS dependent. So this time slice can be, let's say, 1 millisecond or 1 microsecond or 2 milliseconds, 2 microseconds, 3 milliseconds or 3 microseconds, like that. So there will be a predefined time slot which will not change. Once it is decided upon, it will not change. It will be fixed, 2 microseconds or 2 milliseconds, 1 microsecond or 1 millisecond, some time slot. Okay, and once you give the chance for a process to use the CPU or to execute, it will be executed for this whatever the predefined time slot. So if it is for 2 milliseconds, so each process will get its chance to use the CPU for exactly 2 milliseconds. Okay, so after 2 milliseconds that process is preempted, and next process will get the chance to execute again for the same time slot, which is 2 milliseconds. Okay, so this is how every process will get the chance to execute for a predefined time slot. Okay, so this predefined time slot, this is OS dependent, as I told, which is also known as time slice. So execution starts with picking up the first process in the ready queue. It is executed for predefined time. So what will happen? So in the ready queue, whichever process is sitting in the let's say front of the queue or top of the queue, so that will get the chance. So that is the concept of a queue, right? So suppose you go to a movie theater and you want to purchase a ticket, so there will be queue there. So you will go and join the queue. So then what will happen? The the person standing in the front of the queue will get his chance first to get the ticket. So same case here, whichever process is in the front of the queue, or whichever is the present in the whichever is the first process in the queue, that will get its chance to use the CPU for how much time? For the predefined time slot which is already decided. So when the predefined time elapses or the process completes, so there are two you can say chances. Whenever the predefined time elapses, that is, you give a you give the CPU to a process, and that let's say you give the CPU to a process and it utilizes the CPU for the predefined time slot, which is 2 milliseconds. So as soon as 2 milliseconds is elapsed, okay, that process is preempted. Okay, so that may be the first case. Or within that time slot, if that process completes, so then also the process will move out of the CPU, or it will give away the CPU. So there are two chances of preemption. Okay, which one? So one is if the predefined time slot elapses. Second is if the process completes within the predefined time slot. So in both the cases, what will happen? Next process in the ready queue is selected for execution. Okay, so hope you are getting. So there are two chances. One is predefined time slot elapses, or second one is the process completes within the time slot. Okay, so what I mean is, suppose the predefined time slot is 2 milliseconds, so you give the CPU the chance, sorry, you give the process to use the CPU for that predefined time slot, which is 2 milliseconds. Let's say that process completes at 1.5 milliseconds. So it doesn't require 2 milliseconds, it only requires 1.5 milliseconds. So as soon as that process completes, the next process in the ready queue will get the chance. Okay, it need not wait for a entire 2 milliseconds because it is completing before 2 milliseconds. So at whatever time it completes, the next process will get the chance to execute. So this is repeated for all processes in the ready queue until they complete. So once each process in ready queue is executed for a predefined time slot, the scheduler comes back and picks the first process in the ready queue again for execution. So this will go in a circular manner. So let's say there are three processes. So P1, P2, P3. So first P1 will get the chance. It will execute till the predefined time slot. Then after that it will be preempted. Next is P2. So P2 will get its chance to execute. It will again execute for predefined time slot. Then it is preempted. Then P3 will get the chance. So it will use the CPU for the predefined time slot. And after the time slot elapses, it is also preempted. So all the three are done. So then what will happen? Again it will go back to giving the chance to P1 because P1 has not yet completed. It was preempted. So P1 it will get its chance to execute once again, then P2, then P3, again P1, P2, P3. So this will go on until the process completes. Until each process completes. So this is the diagram you can see. So process 1 is given the chance, then for a predefined time slot. After that, process P2 will get its chance to execute, that is use the CPU. So after the predefined time slot elapses, P3 will get the chance to execute. So after the time slot elapses, P4 will get the chance to execute. So after P4's time slot elapses, again P1 will get its chance to execute. So it will go about in a circular manner. Okay. We shall discuss this with the example. So I'll take this example. So this is the example. So there are three processes which are ready. Okay, so process P1, P2 and P3. These are the three processes which are ready to execute. Okay, P1, P2, P3. And so there is an arrival order. So if you remember for preemptive SJF, that is shortest job first or shortest remaining time. So there we have here arrival time, but here there is no arrival time. Instead, there is an arrival order. So it is in which order they arrived. Okay, before the start of the execution, what is the order in which these three processes have arrived in the ready queue? Okay, so the order is 1, 2, 3. That means P1 has arrived first, P2 has arrived the second, and P3 has arrived the last. Okay, and all these have arrived means before the execution starts. Remember this, before the execution starts, all three have arrived. That means at time 0 itself they arrived, but in a different order. That's all. So P1 has arrived first, P2 second, and P3 has arrived third. And what are the service times? So P1 service time is 6 milliseconds, P2 service time is 5 milliseconds, and P3 service time is 2 milliseconds. So these are nothing but estimated completion times. So and we have to also decide on the time slot, right? So let's say the time slot, or it is also known as time slice, is equal to 2 milliseconds. Okay, so all this will be given to you. So whenever the problem is given, so this table will be given in terms of table or in terms of sentence, it will be given, and whatever the time slot will also be given. So based on this, you have to do the scheduling now. Okay, so hope you got the concept, right? Yeah. So now this is the let's say ready queue. So in this ready queue, so what will be there? The processes which are ready to execute. So which are the processes which are ready to execute? P1, P2, P3, and you have to order or organize them in the order in which they have arrived. So since P1 has arrived first, so it will be standing in the front of the queue, or it will be in the first place of the queue. So since P2 has arrived next, so it will be in second place, and since P3 has arrived last, so it will be at the last. This is a queue. Okay. So in this queue, so whoever comes first, that is in this case P1, will get its chance to execute first. Okay. So now, so let's say this is the CPU here. Okay. So what is this? This is the CPU. As I told, I am using a mouse. I don't have pen to write, so bear with me for the writing. So this is the CPU. So now, according to this round robin preemptive round robin scheduling, so in the ready queue, whichever process is at the first place of the queue, or whichever is at the top of the queue, will get its chance to execute first. Okay. So in this case, P1 is in the top, so P1 will get its chance to execute. Right? P1 will get its chance to execute. So here I'll write the execution order, the execution sequence you can say. So at time 0, so P1 is given the chance to execute. Okay, so similar to it. So now, how much time will be P1 given to execute? So that depends on time slot, which we have already predefined, which is equal to 2 milliseconds. So at exactly 2 milliseconds, okay, 2 milliseconds, P1 will be preempted. So P1 will be given the chance only for 2 milliseconds. So since P1 is given the chance to execute at 0 milliseconds or at 0 milliseconds, yes. So then you have to rearrange this queue. Whatever the queue you have here, you have to rearrange this. Since P1 is given the chance, so now what will happen? So this P2 will move up in the queue because as soon as the first person gets the chance or gets the ticket, the next chance is the second person to get the ticket. So that is what. So P1 is given the chance, so P2 will be moved up in the queue. Similarly, P3 will also be moved up in the queue. Now, at 2 milliseconds, what will happen? What will happen? So P1 will be preempted because every process will be given only 2 milliseconds, which is nothing but the time slot or time slice to execute. So as soon as P1 is preempted, so P1 will be entered in the last place because P1 got its chance and it came and sat at the bottom. Okay, came and sat at the bottom. Next is, so now in this case, so at 2 milliseconds, so who will get the CPU? So again, whoever is at the top of the queue. So who is at the top of the queue now? P2. Okay, because you rearrange the queue. So P2 will get its chance to execute. Okay. So at time 2 milliseconds, P2 will be scheduled to execute. Okay. So how much time will be P2 given? Again, it will also be given only 2 milliseconds because the time slot, the time slot or time slice is already decided or predefined. So 2 plus 2 is 4. Okay. So P2 will also be given 2 milliseconds, exactly 2 milliseconds. So again, you have to rearrange this queue now. So you gave the chance to P2. So then what will happen? So you have to rearrange. So P3 will come and sit at the first place. Then, so if P3 moves up, so P1 will also move up by one position. So P1, okay. Then P2 will come and sit at the last position. Okay. So hope you are getting this right. So P1 will come and sit at the last position. So remaining will be shifted up. So that is what will happen again here. So P2 will come and sit at the bottom. So remaining will be moved up. Okay, so hope you are getting. This is round robin because there are only three processes. If you simplify the diagram, so it is P1, P2 and P3. So only these three processes. So they will be done or given the chance in a circular order. So after P3, so P1 will again get its chance to execute. Yeah, so now at time 4 milliseconds, okay, so time 4 milliseconds, what will happen? So who will get the chance to execute? P3 will get its chance to execute because it is at the top. Okay, P3 will get its chance to execute. So how long it will execute? Again for 2 milliseconds only. It will execute for 2 milliseconds. So at 6 milliseconds it will be preempted. So now again you have to rearrange this queue. So again you have to shift up. So this P1 will be shifted up. So P1 will come and sit here. So this P2 will come and sit here. So what about P3? Will it come and sit here? No, P3 will not commence it here. Why? Because you have to keep track of the service time. Okay, you have to keep this in mind because here, so how much time P3 requires to complete? It requires only 2 milliseconds to complete, and you have given P3 2 milliseconds. So from 4 to 6, okay, from 4 to 6, so how much is the time? 2 milliseconds. So hence P3 completes. So since P3 completes, it will not enter the ready queue once again. Okay, it will not enter the ready queue once again. So that is, we can make a note here if you want. So this is P3, P3, P3 completes. Okay, P3 completes. So no need of entering P3 once again. So what about P1 and P2? So P1 requires 6 milliseconds, P2 requires 5 milliseconds to complete. So out of 6 milliseconds for P1, okay, so how much time you have given? So you have given only 2 milliseconds. So still 4 milliseconds are remaining for P1. And what about P2? So out of 5 milliseconds, so again you have given how much time for P2? 2 milliseconds. So still 3 milliseconds of time is remaining for P2. Okay, so hope you are getting. Okay. So now what will happen? Uh, Again, so whoever is at the top of the queue will get its chance. So in this case, since P1 is since P1 is present at the top, so P1 will get its chance once again at 6 milliseconds. So P1 will get its chance. Yeah, till what time? 8 milliseconds. Because you have to give the chance exactly 2 milliseconds. Fine. So now again, so P2 will move up because P1 got its chance. P2 will move up. So now whether P1 will come and sit in the ready queue once again. So that depends on how much time is remaining. So P1 actually requires 6 milliseconds. So out of 6, you have given 2 slots to it. So here, this is the first slot of 2 milliseconds, and this is the second slot of 2 milliseconds. So 2 plus 2 is 4. So it requires 6. So still it requires 2 more milliseconds. So yes, it will enter the ready queue once again because it has not yet completed. Okay, so hope you are getting this because yeah, you have to keep track of the remaining time, remaining uh, completion time, okay, that is required by each process. Yeah, so again now once again what will happen? So whoever is sitting at the top of the queue will get its chance. So P2 is sitting at the top, so P2 will get its chance. Okay, so P2 will be given the chance at 8 milliseconds. So how much time? Again exactly 2 milliseconds only. Okay, so now again you have to rearrange this queue. So P1 will be moved up in the queue. What about P2? Whether P2 will come and sit here? So that depends on service time. So how much time P2 requires for completion? 5 milliseconds. So out of 5, how much you have given? 1 and 2. So you have given 2 slots, right? So 2 plus 2 is 4. It requires 5. That means it still requires 1 more millisecond. So yes, P2 will come back to the ready queue because it is not yet completed. Fine? Yeah, so then what will happen? So P1 will get its chance once again to execute here. Okay? CPU will be given to P1 because P1 is at the top. Yeah, so P1 will be given the chance to execute. So how much time? Exactly 2 milliseconds. So 10 plus 2 is 12. So P1 will get once again its chance. So whether P1 will come back to the queue, that is the question. So whether P1 will come back to the queue. So P2 is remaining, so you have to write P2 here. So whether P1 will come to the queue, that depends on service time again. So it requires 6 milliseconds, and how many slots you give? 1, 2 and 3. Yes, so that means 2 plus 2 plus 2 is 6. 3 times 2 is 6, so and it required 6, so you have given it 6. So P1 completes off at 12 milliseconds. So P1 will not enter the ready queue. Okay, so at this point of time only one process is there in the ready queue, that is P2, so it will get its chance to execute at 12 milliseconds. P2 will get its chance to execute here. Okay, P2 will get its chance to execute. So how much time P2 requires for completion? 5 milliseconds. So out of 5, how many slots you have given? So 1, 2, and this one is 3. So 2 plus 2, 4. So it requires only 1 milliseconds of time. So it doesn't require the 2 milliseconds. It only requires 1 millisecond. That means it will complete off at 13 itself, not at 14, but at 13, because it requires only 1 millisecond. It doesn't require 2 minutes. It completes at 13. Okay. Yeah. So this is what is the schedule. Okay. Schedule for the above example. So hope you got how this will be rotated, right? How each will be given the chance for a predefined time slot. So now, as usual, we have to find out waiting time and turnaround time. So first we shall find out waiting time. So WT for P1. So what is the waiting time? Waiting time is nothing but the time spent in the ready queue by the process until it completes. Okay. Yeah. So what is the waiting time for P1? See, remember all the processes P1, P2, P3 have arrived at 0 time interval only. That is 0 milliseconds only. So they have arrived at 0 only. Okay. Yeah. So P1 has arrived at 0. Fine. And you have given the chance for P1 to execute at 0 itself. Okay. That means waiting time for P1 is 0. So it is not only 0 because P1 never doesn't complete in one stretch. Okay. So P1 doesn't complete in one stretch. So it is again scheduled here and it is again scheduled here. So there will be multiple waiting times. So you have to take the addition of all those. Okay. So initially the waiting time for P1 is 0. Why? Because it has arrived at 0 and it was given the chance also at 0. So it is 0. So 0 plus. So now P1 is preempted at 2 milliseconds because some other process will be given the chance to execute. So P1 is preempted at 2 milliseconds. So as soon as P1 is preempted, it will go and wait in the ready queue. So now you have to consider the time slot where P1 was again given the chance to execute. So in this schedule, when was P1 again given the chance to execute? It was given the chance to execute at 6. So from 2 milliseconds up to 6 milliseconds, P1 was waiting in the ready queue. Okay, so that means, so what is the total waiting time then? It is 6 minus 2 milliseconds. Okay, 6 minus 2, so that is 4, we'll get 4. Again, so once it is scheduled at 6, again P1 doesn't complete here itself, so it is scheduled once again here. Okay, so that means one more waiting time we have to consider. So what is that? So P1 was given the chance at 6 and it is preempted at 8 because some other process wants its chance to execute. So as soon as P1 was preempted at 8, it will go back and sit in the ready queue and it will wait there again. Okay. So until it is given the chance once more to execute. So when was P1 given one more chance to execute? So at 10 milliseconds. So once you give the chance for P1 at 10 milliseconds, it will complete at 12 milliseconds. So P1 completes at 12 milliseconds. That means, so one more waiting time to consider is, so it is from 8 to 10, P1 waited in the ready queue, right? So that means it is 10 minus 8. So this is the complete waiting time for P1. So that means 0 plus 4, 0 plus 4 plus 2. Totally 6 milliseconds is the waiting time for P1. Okay. See it. Waiting time is the total time spent by the process in the ready queue until it completes. Okay. Now come to P2. What is the waiting time for P2? So when did P2 arrive? It also arrived at 0 milliseconds only. Now, but since even though it arrived at 0 milliseconds, P2, it was not given the chance to execute at 0 milliseconds only, but it was given the chance to execute at 2 milliseconds. So it waited from 0 to 2 milliseconds to get its chance to executes. That means so it is 2 minus 0. Okay, so this is the first waiting time spent in the ready queue. So next, again, once you schedule P2, it doesn't complete in one stretch. So it is scheduled here as well as it is scheduled here and it is scheduled here. So it is scheduled 3 times. So whenever it is scheduled 3 times, there will be 3 waiting times. You have to take the addition of all those. Yeah, so it was scheduled at 2 and it was preempted at 4. Okay, so from 4, when was P2 given the chance to execute once again? It was given the chance to execute once again at 8. So from 4 up to 8, it waited, right? So that means it is 8 minus 4. Okay, plus. So one more waiting time will be there because P2 was scheduled 3 times. So now from it was given the chance at 8, okay, and it was again preempted at 10. Fine. So it was preempted at 10. So from 10, again when it was given the chance to execute, it was given the chance to execute at 12. So again it waited from 10 to 12 to get its chance to execute. So that means it is 12 minus 10. So this is the total execution, sorry, waiting time. So it is 2 plus 4 plus, again it is 2. So totally the waiting time for P2 is 8 milliseconds. Hope you are getting this. So next is WT, waiting time for P3. So waiting time for P3. So how many times P3 was scheduled? Only once. So hence there will be only one waiting time. Okay, remember this. There will be only one waiting time. So what is that? So when did P3 arrive? So P3 arrived at 0 milliseconds only. But even though it arrived at 0 milliseconds, since it arrived in the third place, it was given the chance at 4 milliseconds. It was given the chance at 4 milliseconds to start its execution. And once you give the chance for P3 to execute, it completes off at 6 milliseconds. So P3 completes. So it is not scheduled once again. So there will be only one waiting time, which is from 0 to 4 milliseconds it waited. So what is the total waiting time? So it is 4 minus 0, which is 4 milliseconds. Okay. So now I'll use my calculator to find out average waiting time. So average waiting time. So what is our average waiting time? So it is plus 6 plus 8 plus 4. It is 18 divided by 3. So why it is 3? Because there are 3 processes. So average waiting time is 6 milliseconds. So average waiting time is equal to, so you take the sum of all this, it is 18 by 3 processes, it is 6 milliseconds. Okay, so hope you are getting this. So waiting time. Similarly, now I have to find out TAT, or nothing but turnaround time. So if you remember, the assumption was, so the turnaround time, it will have the waiting time plus the execution time or the service time. So that is the assumption. So same assumption will hold here also. So we are not considering the time spent for acquiring the memory, main memory, and there is no IO operation. So you have to leave out those two. You have to consider only the waiting time and the service time. So what is the waiting time for P1? It is 6. And what is the service time for P1? So go back to this table. So service time of P1 is 6 milliseconds. It is 6 plus 6. Totally waiting time for P1 is 12 milliseconds. Similarly, TAT for P2. So what is the waiting time for P2? You just calculated it, right? So it is, I think, 8. Yes, it is 8. Waiting time for P2 is 8 plus. So what is the service time for P2 or execution time for P2? It is 5 milliseconds. So it is 8 plus 5, so is equal to 13 milliseconds. And what about TAT for P3? TAT for P3 is Waiting time for P3. So what is waiting time for P3? 4 milliseconds. And what is the service time for P3? It is just 2 milliseconds. This 4 plus 2 is equal to 6 milliseconds. So what will be the average? So average TAT is equal to, so take the summation of this. It is 12 plus 13, so it is 25 plus 6. So it is 31 divided by 3. Okay, so hope it is correct. Yeah, so it is 12 plus 13, 25 plus 6, 31. So 31 by 3. 31 divided by 3. Sorry, here the entry. 31 divided by 3 equals to 10.33. 33 milliseconds. So this is the weightage, average turnaround time for this example. Okay, so hope you are getting this. So now, so here in the notes that I have given, so one more example is discussed. So again with 3 processes only. So what is the change here is, so P1 service time is 6, P2 service time is 4. So instead of 5 in the example that we discussed just now, so here the service time of P2 is 4 and service time of P3 is 2 again. So time slot is same 2 milliseconds. Just again apply the same concept and see whether you get this schedule that is in the notes, and you get these values for waiting time and average waiting time, turnaround time and average turnaround time. Okay, try this. So we shall discuss about the next preemptive scheduling algorithm, that is priority based scheduling algorithm, in the next lecture. Thank you.